In this video, we will explain the 6 boiling regimens and show video footage of regimens 1 through 5. Our goal is to formulate our own boiling curve with respect to 2 different steel surfaces. Our first surface is a sphere and our second surface is a rectangular prism. We are doing this to see if the shape of a surface plays a role in heat flux. In order to perform the experiment, we would need a way to heat up the steel surfaces to temperatures of 1000 degrees Fahrenheit and up. We developed a small makeshift furnace out of cinder block and charcoal and used an industrial blow dryer to force air into the furnace. We used a Fluke 55-1 infrared thermometer to get temperatures of the pieces of steel and water. Regimen 6 is characterized by delta T values of 1000 degrees Fahrenheit and more. This is the region of the boiling curve the radiant energy comes into play and the heat flux curve rises once again. Because this region requires such high delta T values, we were not able to observe regimen 6 in our experiment. Regimen 5 is also known as a stable film boiling regimen. It is characterized by a vapor film that wraps around the heated object. It appears between delta T values of 900 degrees to 400 degrees Fahrenheit. In the case of the sphere, we observe it fully encased. We believe this is because the sphere is smooth throughout and is better capable of maintaining the vapor film. In the case of the rectangle, we observe the film on the 4 faces, but because of the sharp corners, full encasement did not happen. Regimen 4 is characterized as partial nucleate boiling and unstable film. It appears between delta T values of 400 degrees to 100 degrees Fahrenheit. For both metal surfaces, we see partial film layers collapse and form large bubbles. The rectangle once again experienced these formations on the face of the prism. Regimen 3 is characterized by nucleate boiling and bubbles rising to the surface. In this regimen, bubbles form on the heated surface and then rise to the water-air interface. This stage occurs between delta T values of 100 to 50 degrees Fahrenheit. Because the rising bubbles leave and cause a more vigorous convection, this is the regimen where we see the best heat flux.
Regimen 2 will show the first visible signs of boiling by the small bubbles forming on the heated object in the fluid, breaking off, rising, and then condensing before reaching the surface of the fluid. While in Regimen 1, we can see no visible signs of boiling, other than the small signs of natural convection shown throughout the fluid due to the differences in the densities in the fluid and the possible evaporation on the fluid surface. This regimen's delta T values range from 0 to 10 degrees Fahrenheit. The figure shown depicts the change in the temperature difference between the water and the metal with respect to time. Due to the high heat capacity and amount of water, the fluid acts like a heat sink. The changes in the differences of the temperatures between the metal and the water is almost all due to the decreasing temperature of the metal and not the increasing temperature of the water. This figure displays the heat flux through the objects plotted against the temperature differences between the fluid and the solids. You can see in the figure that towards the beginning of the plot, there is a small dip in the flux that does not follow the trend of the rest of the data. This is due to the film of water vapor that forms around the object for a few seconds, causing the flux of heat to drop before rising again when the film becomes more unstable. This depicts the transition for Regimen 6 to Regimen 3, which is marked on the graph.
During this experiment, we had some errors. One of them being due to some equipment constraints, we had some inaccurate temperature readings. Along with the equipment issues, we had computational error. Computational error included the loss of mass due to scaling and errors calculating our heat transfer coefficients. For calculations, we assumed 2 things: that our temperature would depreciate linearly, and we assumed that all heat is transferred from the object to the water. Finally, we have the fact that physical properties of solids and liquids are functions of temperature. This could also contribute to our computational error. As a final thought from this experiment, we can conclude that the shape does indeed play a role in the heat flux. With the sphere versus the rectangular prism, you can clearly see that the sphere will consistently have a higher heat flux through all the boiling regimens.